Okay, so the idea is not like making a monologue, is having people interrupting, asking questions. The presentation is more just to guide it. It's not too restricted, okay? So please do interrupt, discuss whatever you guys want. So what's the idea of DFaST? We had the if global online, and we had the Cartesi experimentation week, and we've been wanting to do some compelling use cases for a while, which would build on problems that actually make sense to be Web3 problems. And thinking about it, what came to our mind was that the gig economy does have that fit. And why is that? Because if you think about it, it doesn't really make sense to have someone like Uber or Airbnb or all these systems basically matching to parties and being in a position in which they can take like 30%, 40%, 60%, or even more of the deal, right? So let's go to the US. Sometimes the rides in Uber and Lyft would, the driver will only take like 30% of the drive, which is kind of crazy, right? All the costs are basically on the driver. So the idea here is, okay, so we have Web3, which basically makes someone being able to have something that is decentralized, meaning that there's no single party that has power to enforce things on the other party, be it a rate for something that's being paid, like in the gig economy, or saying that you can or you cannot be a part of something, because that's also a problem in gig economy. If you have someone that works driving for Uber or Lyft and they're banned for whatever reason, and it's an error, they just don't get money, right? And they don't get money for as long as that ban lasts. If it's a mistake, hopefully in a couple of days, they can go back to it. But it's not always the case. But then there are a lot of issues with this, right? So in the case of DFaST, we focus then on the ride-share industry. So the ride-share industry is already huge, and it's meant to grow even more. So it's estimated, and there's this article on Yahoo Finance, that by 2013, it will reach $200 billion. So it's a huge industry. As I was saying, there's this problem in which people are getting more and more bothered about the current model. So Uber, Lyft, all these guys, they subsidize most of the trips, but they also spend money in a very reckless way, right? Uber poured billions of dollars on their self-driving program, all this stuff. And now that the investor money dried out, they're trying to revert their finances and also trying to make a huge profit. So the rides that were cheap now are extremely expensive, and they're growing in price. And that doesn't reflect to the driver, because as I said, the Uber, Lyft, all these guys, they're also increasing the rate that they're picking up from each single drive. So what is the idea on making DFaST? Well, let's try to make then a system that's decentralized. There's no middleman that is picking up a lot of money, that's forcing people out of the system based on their own criteria in a centralized fashion. And a huge problem when you try to make this thing decentralized is that, unlike Uber or Lyft, in which all the data is on a server that people don't have access to, when you bring this thing to the blockchain, everything is actually public. So when you make a request on Uber, say you want to go from A to B, Uber knows you want to go from A to B, and that's kind of private, because Uber doesn't allow anyone in the world to go there and check that you just requested a ride from A to B. It just notifies a couple of drivers that it thinks it's a good match for you. And then they actually know there's someone who wants to go from A to B. They accept the ride, then they also get your details. But you don't really have something broadcasting to the entire world, hey, I want to go to A to B. And more than that, you don't have that entire history available. So that's a major challenge when bringing this to the blockchain. How can we design a system that can actually make you come from one place to another, and that you can use reliability every day, but without letting anyone track you and know your habits and know that you leave home at 9 every day to go to work, and then at 5 you go back to work to there, or that your kids study in a particular place or anything else from your routine, right? So in order to do this kind of stuff, we discussed a lot. So here are just a couple of challenges that some already mentioned. That the details should be hidden from the general public, though everything happens using the blockchain, which is a public ledger. That you shouldn't really have the information of all the riders and drivers and all the things publicly available, once again, because of privacy. Another huge issue on making this is that unlike Uber, that has someone on the customer service team that can just arbitrate who's right or who's wrong, how do we do this in a decentralized fashion, right? Because you still have conflicts. You still have issues in which the blockchain itself doesn't have enough info to arbitrate on. So for instance, when you order a Lyft or an Uber and the driver goes and says, hey, the rider is not here. And the guy just is still, I don't know, finding their keys or something like this, and they're not there. But then they lie and they say, no, I was there. The driver wasn't there. How do you arbitrate this kind of stuff? So currently you have customer services doing that. And then it's just Uber from their side saying who's right and who's wrong based on a lot of data that they collect. Like your GPS, your history of rides, your reputation, all this stuff, right? And based on that, they arbitrate what you do. And they slash the party they think it's not right. If you call an Uber or Lyft or something, you cancel. How do you settle who's the right or wrong party? Like, is the driver going the right way? How do you know if there's a detour in there? And he actually couldn't make the designed route, and he had to just go the other way because there's a pothole or the road was closed to film a movie or anything like that. So all these issues, they naturally happen in this kind of thing. And they all have the same Oracle problem, right? Because from the blockchain point of view, you don't have enough data to say if that's true, if that's not true, and who's actually the right party. So another thing that we put a lot of effort is thinking how to solve these things. And we started drafting a DAO for that. Because once again, this is not a limited amount of scenarios. There's always new stuff coming. So we haven't thought of a way to handle all these different cases without putting humans in there. For a couple of problems, we did find solutions. So, and Lina will talk about it a bit later. But we thought about a stage scanner approach in which you can constantly have your phone and the driver's phone signing the position during the ride and agree on that position. And as long as you keep progressing towards your end location, you keep signing this location, and you progressively pay for it. And why do we have that? That's for partial rides, right? So let's say that you're not going to make on time and you give up on the ride. You might be angry that you didn't make it on time, and you might not want to pay. On the other hand, you got a driver that already spent time, that was already spent gas, and that actually spent money, time, and effort driving you part of the way. So it's not fair for the driver to get auto ride, but it's also unfair for him not to get anything. So this state channel based solution can be used to progressively pay the ride in automatically without needing external arbitration. And if this is to be something that's widely used, well, this kind of industry, it has a lot of offer and demand. So that there must be some way to scale the system horizontally. Otherwise, the system won't be successful, right? If you have a decentralized rideshare product in which, well, just 10 people can have a ride at one point, because otherwise you don't have computation resources to do it. So you are all awfully quiet. I imagine you guys would chip in, interrupt, and we can drill down on something. So please feel free to raise your hands and jump on stage or anything.
How about the... Oh, yeah.
Yeah.
Go ahead.
So this is just detailing one of the problems that I described, which is, well, how do we make a system in which I can go from A to B and still preserve my privacy? So you need some kind of commitment on chain, right? Otherwise, you're a passenger, you go and you ask for a ride, and then you cancel it and you don't pay anything because no one can prove that you actually committed to anything. If you don't make this publicly, well, then it's hard for you to actually get matches from drivers and all this stuff, right? So the way Uber works is they know the driver's positions at all the times, basically. So the application on the phone from the driver keeps sending their location live all the time, like every couple of seconds. So when you make a request to Uber, what happens is that Uber has all the drivers on the nearby area, and they have an algorithm that will match you with the drivers and will send a notification to a couple of those drivers and say, hey, you want to take these guys from here to here? If they accept, then it's a match. You get the details of your driver, the driver gets the detail of your ride, passenger, all the stuff, and then it goes. But if you make this web-free, sending this location all the time, you basically have someone tracking you all day long, right? So if you're a driver, you have your location and the history of your location public forever. So people will know your habits, will know where to find you, will know where you'll be, where you'll not be. Let's say someone wants to steal your house, they'll know exactly when they can do it, because they'll know you'll be there or you won't be there based on that public location. So one of the first things we did was invert this logic. So instead of having the driver all the times in there, sending their location, we say there's a ride that's from here to there, and then the driver will fetch the pending driver requests on the area, and will choose which one they want to apply. Okay, so by reverting this logic, we don't have the driver location public all the time, and people can just fetch it whenever they want and can just track the driver. But then we have the opposite problem, right? Which is the passenger disclosing where he wants to go and where he's coming from. So in order to tackle this, the thing we do is that this public request you make on chain is not really fine-grained. It's not detailed. So what happens on this request is that you send a geohash with a low precision of where you are and where you want to go. And how big is this precision? So we established a 6-character long geohash for this, which maps to an area that's roughly a neighborhood. So if you're looking at public data, what you're seeing is there's someone going from Chelsea, and well, they want to go to Brooklyn. And that's all the information you have. And well, based on the demographics and all the amount of rides you have, that's not a lot, right? It's something that can match a lot of people, and but it's enough for the driver to know where he's gonna pick up someone, roughly, and where that person is going. So you're interested in doing that, great. You accept the ride. When you accept the ride, what happens is that then the passenger will actually disclose the route to the driver. Okay, but how do you make sure that that route is actually what the driver was supposed to do? Because when we do these requests saying, hey, I want to go from area A to area B, we also put the amount we're willing to pay and the distance. So how do we validate this? So the Cartesi machine has this interesting process that you can do through an API called inspect. What's this inspect? This inspect is running some computation that won't change the state of the application. It's read-only. And you can use it to compute whatever you want, to query data from the state of the application, so whatever you want. So the way we figured this is, okay, we can put a routing engine inside the Cartesi machine, something similar to what Waze or Google does, Google Maps. When you want to go from A to B, you say the places, and it calculates a route from one place to the other. These are classical routing problems. There are multiple algorithms that are used to do this. So Dijkstra is one of them. You can use other graph navigation algorithms to do this kind of stuff. And there's a very popular open source routing software that does this. That's called OSRM. And this OSRM generally relies on public data as the graph in which it navigates. So in this case, we use OpenStreetMap's data. So what we did is we baked OSRM inside the Cartesi machine with OpenStreetMap data. And with this, you can use the inspect in the Cartesi machine to make this read-only call saying, hey, what would be the route from where I am to where I'm going? And then you have the Cartesi machine making this deterministic route, reproducible route, from point A to point B. And when you make this request that you want to go from one area to another, you also put a signature of this detailed route that you requested to the Cartesi machine. So though you're not revealing your route when you're making the request, you're committing to it. And when the passenger sends the detailed route to the driver, he can go back to the Cartesi machine, do that exactly the same inspect that the passenger did, and he can check that that route is exactly the one that corresponds to the signature that the passenger sent when he made the request. So this way, you will have a very detailed route that you don't disclose beforehand, you just commit to it. And you commit to it so you know how much you're gonna pay for the ride and how much the driver will take for it, the distance. And then the driver can just validate and check, hey, this is actually the ride I committed to. This guy is not changing it to a longer route or changing the destination or the origin. Everything is in place. And once you have this, then, well, the driver is ready to pick you up where you were supposed to be and take you to your final location. And there shouldn't be any disputes on how long the route is or how much it's going to pay, because everything was laid beforehand, and the driver was aware that he was going to drive X kilometers and was going to be paid Y for that route. Okay? So I just packed a lot of information here. Are there any questions, doubts? No? Okay.
As a question on the chat from
Yeah.
Anderson.
I'm sorry.
Is asking if all the mapping routing data needs to be inside a Cartesi machine.
You don't put the map itself. So OSRM ingests, it has a tool that ingests the map itself, and then it builds the optimization table, right? This optimization table is based on the map, but also on the profile of what you're using to generate it. So in the case of DFaST, we used the default Lua script from OSRM that is used for cars. So this thing basically has the speed, the weight of the vehicle, all this kind of stuff. And it's used to calculate this routing table, considering all these things, right? If you use a truck one, for instance, it will yield different values because it might not use the same bridge it will use with your car, for instance. You might have a city that has limitation for large vehicles during daytime, all this kind of stuff. So OSRM actually works on top of this optimized table that's derived from the script that describes your vehicle and the public map data. But yeah, this file is inside the Cartesi machine, this routing table.
Yeah, but the thing is, you need a reproducible route, so the driver can build the same route as the one that the rider did. Otherwise, the signature wouldn't match. So that's why it's important to be at least on a deterministic environment.
Yeah, so I haven't extensively tested, but I don't think that OSRM routes are fully deterministic. So putting inside a Cartesi machine is a way to make sure that when you make that commitment, it's gonna match with the verification from the driver. I see you're still typing, so I'm gonna wait a bit to check your next question.
There is another one.
Yeah, that's a great question. So it's actually really hard to do it. So one way to do
Carlo,
this.
Just please read the question so everyone can take.
Yeah. So Anderson's next question is about real-time data like traffic jams and this kind of stuff, if that's possible to update. So as I was saying, this is a really, really hard problem. So the way these things are handled is by average behavior. So you know that there's going to be usually a traffic jam like in rush hours. So what you do is you can have different Cartesi machines in which you use to inspect the route. And that's separated by time slot. Okay. So for instance, you crunch the data of traffic into 15 minutes time slots or something like this. And based on that, you have different weights on each segment of the street. And when you do this optimization that I just mentioned, that OSRM just crunches the data of a vehicle profile to make a routing table weight for each segment on the graph. These weights will have different values based on the time of day, and that accounts for traffic as well. So basically what you have is you shard time-wise the instance in which you're going to use to check a route. So if it's like, I don't know, 1 p.m., which there's no traffic, you're going to get a route that goes through the main road, for instance, and that's shorter. But if you go like 5 p.m. or some rush hour, you might have a route that goes another way because there's going to be a lot of traffic in there. That route is going to be longer and it's going to cost you more. And it's also going to take more time because you're going to do a detour. We haven't made it yet, but that's the solution for this. Basically, you have to separate multiple instances with different tables that are used for particular time windows.
Also, a small note on that is that when the route finishes, the driver and the rider they send messages on the position and the timestamp they agree on that the trip ended, and then the system can correct the payment of the final payment of the ride. So since all the assets are inside the dApp itself, they can do that. And since both they agreed on that final position, they can adjust the final payment.
Okay. So any more questions about the routing part here?
I have one. So in the end of the ride, could you update the real time traffic based on the time it took for the ride to finish? Something like that?
So update, I don't see this as real time. The real time part can be on demand and offer of rides, but the actual traffic part, it's more like an off-chain processing, and you keep updating the model based on the historical traffic from the instance that you use to check the route. So that's
Also,
how
if
it
you
works.
change if you update these things during the ride for someone who just submitted the ride and the driver is checking could have a different result. So it's important to not change the model between the middle of the request. Right?
Because once again, you have to agree on the premises to calculate that thing. It could be too deterministic. Okay. If there are no more questions, then I'll move ahead here. So this is just showing a quick test on the Cartesi machine. So we made this simple Python script that goes and does an inspect on the Cartesi machine, asking for the route from point A to point B. And once you get that on the OSRM backend on the Cartesi machine, it just answers a huge JSON that's very detailed, and it has all the information that you would get when you use Waze or Google Maps or stuff like this, right? So in this last portion here, we have the distance on the last segment of this trip that was from Rio de Janeiro Center to Botafogo, if I'm not mistaken. You see the name of the last street in which you go, which is Guilherme Naguini Street. The location on GPS, the distance, which is in there, all the stuff, right? So that's just to illustrate it. Another really important point on this system is reputation, because when you have these ride shares and also gig economy in general, you need to make sure that you have someone that's not abusing from the system, right? So one of the solutions for that is having a reputation system. So if you're a good actor, you keep using the system correctly, you should have a high rating, and then people will have more trust that you actually won't bring them problems, that you actually do your part. If you're a driver, that you will actually take the person from one place to another, that the ride will be comfortable, that there are going to be no issues. If you are the driver, you want a passenger that won't wreck your car, that won't get drunk in there, puke all over it, or any other issue that might prevent you from performing your job, right? If someone pukes on your car, that's the end of the day for you. You cannot drive any longer, right? You have to spend quite some money having it really well cleaned and all the stuff. So not only you won't get money, but you also have costs, right? So for the reputation system, once again, a huge challenge is, okay, so how do we make this in a way that's not identifiable? Because if you just have a ride from point A to point B, and when it's concluded, the driver gets points for it, and then the passenger gets points to it. Well, then you just have to look at the reputation of the person, and then you reverse engineer who they are, where they were, all the stuff, right? Because you'll see that, I don't know who made this ride, but Lino just got the points for all these rides that are coming from here up to here. So I know that's Lino's route, right? And I know he comes from work to home or anything like that, or from the gym to his brother's house, or all his habits. So in order to do this, we have this system that decouples earning the reputation and submitting the reputation to your score. In order to do this, we use these zero knowledge proofs. And Lino, you want to explain this? It's a bit like the idea that's used on Tornado Cash, for instance.
Yeah, so the end goal here is to have a kind of ephemeral wallets. So you can use once, do the ride, and also serve the ride as a driver, and just abandon that wallet. So you would never be traced back to your own wallet, and people will never use the public information to find you. So that's the end goal. For that, we need basically two things. So we must keep some kind of data inside the system, just to have the security of the system, as the Carl was describing. So you check that the driver is doing the right thing, and so when you're going to choose a driver, you choose the one that it's more trustworthy. But how do we do this with these ephemeral wallets, right? So for this, we created this ZK verification, in which you can export the reputation you have using the zero knowledge proofs, and then import. So for this, we have two zero knowledge verifications. So the first verification, you do a commitment of the reputation you have with the secret information, and you verify that the commitment that you did was indeed tied to the reputation you actually have. So this is the first zero knowledge verification. The second one is when you are this commitment is Merkleized. And so the second one, when you import the reputation, you check that the commitment that you did is indeed on a Merkle tree with that specific root. So this is reminds the Tornado Cash approach, but it's a little bit more complex because it has more steps to it. But this approach comes with several challenges as well. So if you can export and import the reputation, you could sell the reputation. So there are some efforts to discourage this kind of behavior. So if you're a driver, when you enter the system, you should pay some kind of secure deposit that you can only withdraw when you have the amount of trips that you did. So that it encourages people to stay with the same wallet, so they won't change when they have a bad reputation. And also an important thing is people can deny the reputation they were given once the trip is finished. That's because they would have the locket amount, so this would be discouraged as well. And also we didn't implement this on this POC, but another problem is the payment itself, because you would have the assets inside the dApp, but you probably don't want to deposit each ride using a different wallet. Also for the driver, you would have to withdraw the money when you're changing the wallet address. So the end goal would be to have a zero knowledge based payment system such as the Tornado Cash. But the thing here that we have to avoid is money laundering. So we have designed some things to discourage this kind of behavior as well. So you would have two different systems. One for the someone who is paying, the other one for someone who is earning the money, the driver. And you only would be allowed to withdraw if you are drivers, if you have money on this withdraw zero knowledge payment system. So, so other things to discourage people to change their wallets, to change their reputations, is each driver pays some kind of insurance according to their reputation. So if they keep the reputation, if they change their reputation, if they keep their reputation high, they are advantaged on that. So anything that I forgot, Carlo?
No, not that I think of. So you spoke a lot about this pretty complex system. Any questions?
I have one. I would like to know more about the experience of using Aztec Noir within the Cartesi machine. Is it
so? So more details on how we did this. We use Aztec Noir language to create the zero knowledge programs, and the Aztec Noir, its syntax, it's like Rust, and they have some standard libraries which eases the development of the zero knowledge. So you don't have to code like the Circon only multiplications. You can do high level you use high level functions such as Pedersen hashes. But since we wanted to tie with the Merkleization inside Python, we used SHA library, they have on Aztec Noir, but we had to code everything around to tie the PyMerkle with the Aztec Noir verification. So there was a little bit of work, but using this kind of high level language as Aztec Noir, the development is very facilitated.
But the verifier itself, the verifier is the one running inside a Cartesi machine, right?
Yeah. So Aztec Noir, they have tools so they have a command line tool to compile your circuit to some kind of binary. They have they also have proving and verification tools, and also they have they can generate code, solid code, so you can verify the zero knowledge inside in Solid itself. Yeah, but so they have all these tools, and also they have the analogous for JavaScript. So you can do the proofs on the browser or anything that uses JavaScript. And so the whole ecosystem is very tight. So the POC, we just use the command line tool. So the proving is not on the front end right now. but it will be very facilitated by the implementation using JavaScript. And what we used, we ported this verification, command line verification to the Cartesi machine, and proved and verified the zero knowledge presented there from the Python our Python backend. So we just do a process to run the tool. We have created a small example using this integration on our GitHub. There we can put here in the shop in the message box. If we have some time after, I can show how it looks like. But yeah, it's I don't know. I'm not much of a Rust programmer, but it seems to me that's very similar.
So this is just a record of this process of using this zero knowledge to import and export reputation. And is running this code of the backend here. Code and then the verification.
Could you maximize the part, the video itself, because it's very small, just a part of the screen for us?
Yeah, just a second. It's opened on the wrong browser, sorry. Better?
I guess just showing how the code looks like, and also the number of gates that the code generated these two reputation systems, zero knowledge verifications. The second one, which it's checking the Merkle. I have a commitment that it's inside the PyMerkle hood. The PyMerkle tree, I couldn't put on Solidity. It was too big for that. So with this we allow this kind of huge and complex verifications as well, because we are inside Cartesi machine, right?
Any more questions about this ZE part? Nope. Okay. So, as we said, there's a lot of things that we want to see improve, right? So for the scope of the hackathon itself, we wanted to have a direct message protocol between driver and rider. And that's like messages, like real text messages, WhatsApp like, right? So when you're talking to the driver, like, hey, I'm here, can you meet me on the other side of the street or something like this? For the scope of the hackathon itself, we thought about using this XMTP protocol, which was on one of the tracks and allows you to send direct messages using your public Ethereum address. Another thing we want to implement, but we don't have the time, is implementing ride price multipliers using things like weather, for instance. And for that, we could use, for instance, the Chainlink Oracle to fetch periodic updates on the weather, on the region, if it's raining, if it's snowing, whatever, and apply a multiplier to the price for that. There could be a special multiplier for the price for if there's some city event or or if there's a public holiday or things like this. But those are things that are better decided by the community, let's say. And all these conflict resolutions for things that might come and are not straightforward to understand how to solve them, they still need the human element, right? So a DAO is a must to solve these kind of things, right? You can have an off-chain forum in which people present the evidence and all this stuff, and then you have DAO members arbitrating what's the correct outcome. That way the process is more transparent. And our idea for this DAO is that this DAO would be used not only for the conflict resolution, but also to set the parameters of the system. So when you have Uber or Lyft, they just say how much it costs per kilometer, how much it costs per time in which the guy spends on a traffic jam, or the multipliers when there's a surge, all this stuff. It's all defined by the companies in a centralized fashion. But being this a Web3 system, all these things can be decided by people with a stake on the protocol itself, right? So this DAO can have proposals for increasing or decreasing the rates. People with a stake on it will probably want to make it work, right? So you should have an equilibrium between riders and drivers. Drivers would have a natural desire to raise rates as much as possible. Passengers on the other side would want to decrease them as much as possible. So all these conflicting objectives should reach some equilibrium in a point in which drivers can actually work and keep up with these costs and have enough profit to have a good life. And on the other side, passengers should have a rate that's not high enough that it's not worth it. It's better to get a cab or to have your own car or something like this, right? Another thing we imagine and we discussed a lot, but we didn't have the time to do it, is implementing a decentralized insurance protocol. So based on a reputation system, you could have a really expensive deposit you should make for insurance if you're a new rider or a new driver, and that could get progressively low in case your reputation increases, right? So if you're a really high reputation driver, for instance, you should have a low insurance overhead on your ride. And this decentralized insurance protocol would cover for problems during rides, right? So if you have an accident, or if you have a passenger that wrecks your car, all this kind of stuff that is not usual, you could have this treasury that would pay you, and once again arbitrated by the DAO. So you would present the evidence to the DAO that your car was damaged, or that you were on involved in an accident or anything like that. The DAO would arbitrate and would pay you the collateral needed for you to cover your expenses, right? Which is also another very important aspect on turning this into a product. And another thing is to keep the system health and sane on all those rates and all this stuff. We imagine that people with a stake to vote would also have some return for it. Like on each ride, the protocol would have a small amount, like 1% or something like that, of the rides that would go to this treasury to reward people that have a stake on the protocol. And once again, this return would be defined by this DAO, right? So if the community decides that the rate is too low, they can raise it. If the community thinks that the rate is too high, then they can it's too low. Sorry, they can raise it. So those are some ideas that we had on how to make this a viable product that weren't implemented yet.
Also, onboarding non-native users, we could have the whole system using relays, so people wouldn't have to be using Web3 wallets, and everything will be just handled by the front end. And people would just have to make an initial deposit, or if they want, they could hire from they could buy credits from the dApp using credit cards. That's one piece that they would have to trust, and that is a big part of where developers could actually make some money on this conversion, but it's optional, right? And that way, they wouldn't have to use all the hassles, be subject to all the hassles of using Web3, because the front end itself would handle all the transactions, change the wallet when it sees feed, and yeah, I think it will be just a very clean and user experience.
Okay, so I think we covered most of the challenges and the things we fought. There's also a huge discussion that we had about how to make this horizontally scalable. We touched a couple of the points on the solution. So a lot of the load of the system is figuring out the routing and all the stuff. But since we were able to make this as an inspect, then that naturally scales horizontally. You can just have multiple instances to calculate that kind of stuff. More users, you just put more instances in parallel in order to keep up with the demand of calculating these routes. The matching itself, it's not done server side, it's done on the front end. So what the system actually has to serve is the list of pending ride requests. So that also lowers a lot the load on the server side, let's put it this way. It also helps to scale. Another thing is that since we took this approach of using geohash, we also use this to segmentate the areas. So you will have different DFaST instances taking care of different areas, right? So you won't see all the requests for all the rides in the world. You'll see the requests of the rides of your area, like your city, or if it's a countryside or something, then it can be something larger. But yeah, you can set this granularity to something that makes sense. And we decided that we would map the person based on the origin. So it doesn't matter how long your drive is, you're always gonna post it on the origin server. Okay. And then if you make some ride that's not reasonable, something like, I want to go from East Coast to West Coast, the drivers will simply ignore it. Okay.
So in the end, the interaction with the dApp itself, it's not that much, right? You have the deposits, of course, and also the request and request for drive, answer for the drive, and then finish the drive. It's essentially that.
So yeah, guys, I guess that's it. Any question, comment, doubt?
there's a comment in the message box from Barros about doing root hash calculation in browser using the WebAssembly build on the Cartesi machine. What do you think about that?
We haven't tested it, but yeah, it's a possibility. That would further lower the overhead of the server side, let's say. So yeah, it would also help decrease the cost and scale the system.
Yeah, let's keep in mind that the end goal is to have this dApp is running on a mobile system, right? So yeah, we will need that too.
Yeah, but we haven't tested how much alpha hassle it would be. But yeah, it's a nice thing to try for as a next step.
In any case, we'll be always available for answering questions asynchronously. So yeah, if you think of something later, yeah, please.
Yeah, and if you're interested in contributing on this, just send us a message.
Maybe it could be interesting to share the link for the source code.
Sure.
That's it, Milton.
Yeah, that's it.
Yeah.
As a closing note, then, well, are you going? Please, if you can close. Yeah, I think Lynn is going to post some links there. Carlos just did. So we hope we can bring some other of the projects from the experiment week to have a deep dive inside. We'll keep you posted about that. They're already making rides there. So I guess that's it, guys. Thanks a lot for tuning in. Any closing note, Claudio?
No, just to give congrats to Carlo and Lino. Nice presentation, nice work, and inspiring the app for the community.
Yeah, don't forget about Artur and Claudio as well. It was a four-man team, so yeah.
Yeah, thanks Artur, Claudio. Bye-bye, guys.
See you guys. Bye-bye. Thank you.